today. So I mentioned this to Michael, but I'll mention it again. My son is here with me. So every once in a while, there may be some loud proclamations about a cartoon. So we'll just let that be. If folks would like to turn their cameras on, because sometimes it's nice to see a few faces when you're talking, that's great, but no pressure whatsoever, whatever is comfortable for you. So today I'll be talking about a fresh look at introductory data science. So what do I mean by this? So the questions that I'm trying to answer here is, how can we effectively and efficiently teach data science to students with little to no background in computing and statistical thinking? So when I say introductory data science, I do genuinely mean that we're looking at a student who might be in their first year of university and first semester. And how can we equip them with the skills and tools for reasoning with various types of data and leave them wanting to learn more? So the goal for this course is to meet students where they are, and that might be that they've literally just arrived at the university, and then bring them to a point where our goal is not to teach them everything, but we at least want to see, would they be interested in taking another statistics or data science course next? My goals here is to demonstrate concrete course examples in this talk, share a few tips about teaching such a course, and also provide some open source teaching resources. Just based on my area of interest and expertise, I often find myself in pedagogical talks about folks talking about how they teach their courses. And personally, for me, it's really nice to see concrete course examples to ground what we're talking about. So I hope you'll find those enjoyable as well. So what we focus on in this course is data visualization, and that's the first thing that we teach students. In fact, they are learning R as the programming language in this course. And instead of telling them really so much about even what R is, how the R syntax works, or anything like that, we start getting them doing a data visualization. They do their first data visualization within the first 15 minutes of the course, actually. And that's kind of the goal. You kind of try to create the computational environment that allows you to do that. And then through the language of data visualization, by using the syntax for building these data visualizations is how we teach them about things like, what is a data frame? What is a variable? What's an observation? So all of that elementary stuff happens within the context of data visualization. And then we take a step back and say, well, what if your data isn't really ready to be visualized, or at least in order to do something interesting to visualize it, you need to maybe wrangle it a little bit, tidy it a little bit, or in fact, perhaps find the data where it is and import it, whether that's like a CSV file that happens to be sitting on somebody else's computer, or something like web scraping where you need to harvest the data and put it together. After we have the data all in one place, then we talk a little bit more about exploratory data analysis as a whole. So initially, these are like visualization, wrangling, tidying, acquisition are separate kind of topics. And then we bring it all together to see, you have an objective, which is to explore this data. How do you put into practice everything you've learned so far? The next unit is about modeling. So we start with modeling and take a predictive approach to it as opposed to an inferential approach. But as a statistician myself, I don't necessarily feel right going through an entire semester of doing anything with data that is, gathered in a myriad of ways. Some of it actually random samples, some of it just convenience samples off the web, and not talk about uncertainty quantification. So we certainly touch on that as well, in the sense that when you make a prediction with a model, thinking about, we found now a single number. What does that number mean? What is our confidence bound around it? But we don't actually go into a whole lot of traditional introductory statistics topics like null hypothesis testing or building confidence intervals using the central limit theorem. In fact, the uncertainty quantification aspect of the course spans only a short time, and we primarily focus on bootstrap intervals, just basically leveraging the fact that they feel comfortable with computing at this point, so they can write the code to do the bootstrapping, and they've already done things like cross-validation. So at this point, it's not computationally not a big ask to teach them how to do bootstrap intervals. And then within the context of that, talking about why do we care about uncertainty? but certainly not doing it a full justice in terms of what a student would be able to say, I know a lot of statistical inference. And the goal here is to leave them wanting to learn more to what might be a slightly more traditional statistics course at the second or third level, where they'll not only learn things like the central limit theorem, but probably do so with the appropriate mathematical grounding as well. Another theme that runs through the whole course is effective communication of results. So there's at no point are students doing something only computationally, like make a plot, build this interval, find the RMSE. They always have to interpret whatever they found within the context of the data. And ultimately in the course, they do a big project at the end as a team. And there's a lot of communication aspect of that to that as well. We do foray into things like interactive visualizations, a little bit of text analysis, some machine learning, even a bit of Bayesian inference in the context of kind of decision making. But I would say that I've purposefully put these under foray into as opposed to focus on, because we spend the last week of class or the last 2 weeks, depending on the length of the semester, just touching on these things bit by bit, to show the students what more they could do if they were to take more courses or do a project or something like that. Some of the emphases are in the course from a computational perspective is we use a consistent syntax all throughout the course that's tidyverse focused. And what that means is when we get to predictive modeling, we're doing things with tidy models. When we get to uncertainty quantification, we're taking our bootstrap samples a particular way in a pipeline as opposed to, say, writing for loops. So everything stays consistent throughout the semester. Another big emphasis is reproducibility. So everything happens in an R Markdown document from day one. Every single report students turn in or a homework assignment is an R Markdown document. And in order to be able to make this happen from day one, what we do is we provide them a template R Markdown document that almost feels like fill in the blanks during the first week of class, and slowly taking away that scaffolding where at the end of the semester, when they work on their big project, they just have a bare document to start with. Another theme is version control on collaboration. So everything is version controlled in the course, and every assignment happens in a GitHub repository. The way this is structured is GitHub has this notion of organizations within which you can have private repositories. So students work there. So we're not putting their work publicly out into the world, but we are able to control it in a way where all the instructors can see their repositories and mark their work. And also for any teamwork, we're able to give the appropriate access level to repositories. This is a lot of computational stuff happening, especially when you think about them happening all in week one of class. So there's a lot that's new thrown at them. And the way all of this is made possible is lots of logistical work on the side of the instruction, preparing template repositories for them, giving them the right level of access. So really all they need to do to start is things like grab the URL, clone it into RStudio, knit your document, and there you go. You've already done half of your homework in the week one of class. And again, these training wheels come off throughout the semester where they really learn to do the full data science workflow on their own. But for at least the first few weeks of class, there's a lot of hand holding happening as they're learning the syntax. The topics in the course is, starting with a hello world where we talk about introduction to all of these tools. Then we have the exploring data unit, which goes visualize, wrangle, and then import. Then we have a unit on data science ethics. So the exploring data unit is roughly 3 to 5 weeks, depending on the length of your semester. Then there's a week of data science ethics, where right after we teach them how to do web scraping, and having already told them at least once, just because you can scrape the data doesn't mean you should scrape the data. We start talking about things like data privacy, misrepresentation of data, in especially like data visualizations this year. This was a very easy topic to teach with all the COVID visualizations, for example, that we have seen over the summer. And also talk a little bit about algorithmic bias and this notion of, if you have biased data in, you're going to get biased results out, before we actually dive into the topic of modeling, and especially predictive modeling. So in the To give you an idea, there are many ways you could be teaching algorithmic bias. One of them is actually teaching the algorithms and the implementation that goes with it. That's not what's happening in just a week. That wouldn't be realistic. But at least there's a lot of forewarning happening in that data science ethics course. And especially that week is a time when students are putting in their project proposals, where they find a data set of their choosing and pitch a project idea for their team to work on. So as they're working on that, we want them to think about not only can I do it, but also should I do it as well. In the Making Rigorous Conclusions unit, we start with what is a model? What does it even mean to model the data? How do we build predictive models? And then finally doing a little bit of statistical inference with mostly bootstrap intervals, as I said. And the last unit is really your playground. Again, that's 1 or 2 weeks, depending on the length of the semester. And that's when students are expected to not really implement what they're learning at that point. We have the notion, for example, here at the University of Edinburgh, that in week 11, we don't teach them accessible material, for example. And that's when I actually ask students to vote on some topics they might want to learn about, and then we bring those into the classroom. But really at home, they're working on finishing their projects as opposed to trying to put into practice what they've learned. But at least during class time, we're hopefully able to open their eyes to something new that they might take a next course in within their curriculum. So let's start with the visualized topic. So how do we start the class? So the day 1 of class, one of the data sets that I like bringing into the classroom comes from United Nations vote. So this is records of voting from the General Assembly, United Nations General Assembly, over many years for many countries, for many issues. And what do students do on this day? They basically they're instructed to go to, I've been using RStudio Cloud for my teaching, but this could be any kind of server instance of RStudio. The key being that it is not a local installation. That is not what we're doing in day 1, because then we couldn't get to the first visualization in 15 minutes. It simply wouldn't be feasible. They start a project and open an R Markdown document and knit the document and review the data visualization that they just produced, which looks something like this. So this is, we have the voting years. Many countries are in this data set, but I've subsetted them for a few countries of interest to me. I'm originally from Turkey, so that's one of the countries that I pick. I lived in the US for many years, and we're in the UK right now. So those are the 3 countries I used last semester, for example. And we asked them to first interpret what we're seeing here. And the nice thing about a data set like this is you don't need to know a whole lot about politics or world issues, but you probably can understand how different countries might vote on things like arms control versus, say, the Palestinian conflict. And so what they're seeing as results here does not fly in the face of what they would expect to see, probably. And then we tell them, you have an R Markdown document in front of you. Make one change to it. So next time you knit the document, you're not seeing Turkey on the plot, but another country. So at this point, students pick something of interest to them, either a country they're from or they've been to. And when we do in-person teaching, that's a really nice icebreaker opportunity, because we ask them to, talk to their neighbor about why they picked that country and how they voted. But under the hood, what's happening is they've actually written their first piece of code. So in terms of getting this working, this requires that we have server access. So everything is set up for them, the computational environment, that we have a fully functioning R Markdown document where creating the visualization is simply pushing one button, which is knit. And then the third thing is looking at a big chunk of code that would create this visualization and be able to say, can I be brave enough to make a change to this thing that I don't understand at all, where all I'm doing is changing the word Turkey to another word like France or Italy or China or something like that. And that basically is the sort of thing that we want to teach students to be comfortable with experimenting. A lot of times when we're teaching programming, or really anything else, but it comes up a lot in programming where students say, what if I did this? Would the code work then? And the answer often is, well, just try it. You know, you don't have to pay by the line of code you run. There is no harm in trying it, and you're not going to crash and burn your computer either. But these things feel so obvious to us, but not necessarily very obvious to somebody who hasn't written a line of code ever before. So the idea is to get them kind of be comfortable with experimenting. So when I say they make their first data visualization in the first 15 minutes, I'm on one hand not lying at all, but on the other hand, actually kind of not really talking about creating a data visualization from scratch. What I mean is they reconstruct something where we've given them fully functioning code for in a computational environment that we already know is working for them, and asking them to change one line of code. But from their perspective, have they made a new data visualization with a country of their own choosing? And the answer is yes. This past semester, when I taught this class, I gave students an option to also, instead of working with the UN data, also worked with COVID data as well. I didn't want to impose it on everyone because, you know, it's still just very raw, and working with things like COVID fatality data may not necessarily be the most pleasant way of starting a class for every single student, but for some of them it's interesting. So you might think about what are some accessible data sets that everyone will know a little bit about, but also think about potentially how sensitive the topic that you're talking about might be. Another example I'll give is from the data wrangling topic. So here we have data on fisheries of the world, and the data actually comes from Wikipedia, which is a place where a lot of students go, you know, see data kind of shown in a tabular way that looks like what we call a data frame elsewhere in the class. And also they often use as a data source for their projects as well. And these are some visualizations based on these Wikipedia entry about like how much fishing harvest happens in each of the countries. And these visualizations were provided to me as part of a consulting project. In fact, I was able to update these visualizations in Excel because turns out they're very easy to make in Excel. If you have the data like in an Excel spreadsheet with countries for each row, and then we have 2 columns for each country, sorry, 3 columns, the total fishing harvest, farm fishing, so what they call aquaculture versus capture. The thing is, these are not good visualizations, obviously. I mean, already we say a lot about pie charts not being good. I think 3-dimensional exploding pie charts where each pie is a country where you can't even tell the colors apart are clearly not useful. So they're kind of so bad that they've become a nice foray into talking about how we can improve data visualization. So we start with these and start the conversations around what would you like to do with these data? And one of the first things students land on is, well, we have country data, but we don't have any spatial information presented to us in this data set. So how could we actually capture that, the geographic information? So this becomes an opportunity to teach something about data join. So we have data on countries, and then we bring in data on continents that we get. I think the data source for that is the UN, and then make that an opportunity to teach how do you join data. When you join these 2 data sets, though, you see that some of the countries do not match between the 2 data sets. And if you look at the countries that don't match, they might make sense because some of this is because the country's name might be represented differently, like Myanmar, for example, tends to be represented differently depending on the date the data was compiled. Some of them are actually a little bit more political. Not everyone necessarily thinks each of those countries on that list should be considered a country. So the notion of what is a country is not an obvious thing. And also Congo just has a very long name. So like whether you use the long name or just the word Congo changes from data source to data source. So not only is this an exercise in data cleaning, but it's also an exercise, an opportunity for us to make an ethics statement that every time you make some assumption about the geographic boundaries of a country, you are actually making a a decision yourself and potentially bringing in something that you believe in into the data source. Then we go back to actually cleaning the data, joining the two data sets, and then creating something like this bar plot where we're looking at the average share of aquaculture by continent. So how much farm fishing is happening in each of the continents that we created. So now we can actually critique the first visualization and improve it and talk about kind of visualization improvements. If you're familiar with ggplot2, you'll recognize that the bar plot at the bottom, as simple as it looks, is not the default look. We've changed a few things. We've annotated in a few ways. We've, for example, created a short link for the data source and whatnot. So each of these are actually presented to the students in an incremental fashion. So we can talk about how do we start with what we have on top and end up with something a lot easier to parse through as the reader. This also becomes an opportunity to teach mapping, which means we talk about what shape files are. We talk about how do you represent polygons on a map, and also talk about things like maybe log transforming data and whatnot for better representation. The next example I'll give is from the data import unit. So this was a fun example to work through. We teach data scraping, and I wanted to bring in something about COVID. So this past semester, I brought in some data from the First Minister's COVID briefings. So Nicholas Sturgeon talks like every other day at 12:30 p.m. and gives a briefing. Probably one of the world leaders who I've seen give like so many briefings so regularly. And there's also, if you ever listen to her talk, there's a very specific cadence to how she says certain words. Always opens in the same way, always presents the statistics with the same way, always says something about these are not just numbers, these are human lives, and then goes on to say something about the policy changes. So each of these briefings are provided on the ScotGov website. So here what we talk about is how do we scrape the data. But before we do, we talk a little bit about, are we even allowed to scrape the data? So we talk about the notion of what's the robots.txt file that exists in every single web page, and how do we access the information on there using R to just check at a minimum, are we even allowed to scrape these data? Happens to be yes, the Scottish government allows you to scrape these data. So we go on to talking about how do we get different aspects of each of the pages for the speeches. So this is where we can talk about web scraping in general. Text parsing, you can see things like dates or the location are kind of text strings that we might want to parse. We get to talk about data types, again, things like characters, date types, maybe factors. And we also get to talk about regular expressions, because soon as you start working with text data, there obviously comes a point where you need to talk a little bit about how do we actually parse that information out and get it into a tabular format. So when I say regular expressions, we're obviously not covering everything there is to know about regular expressions. We couldn't, because I don't know everything there is to know about regular expressions. It's something I have to Google my way around a lot. But it is an opportunity to show to students what we're seeing on this web page does not look like a data frame at all. However, we can use this web page to create a single entry on a data frame, which is basically some metadata about that day's speech, and then the text of the speech itself, and then iterated across many, many pages to basically create a data frame where each row is one of the speeches. So here we talk about, once we scrape one of the web pages, how do we write a function to do that instead? And then how do we iterate across each of these entries? So we use the per package for doing that in R, which means we're actually doing functional programming. So as opposed to writing, say, for loops to go through it. But from the student's perspective, they don't necessarily need to think about this as opposed to doing for loops, because we've never actually taught them for loops. So when I said earlier, we use a consistent and opinionated syntax, it really is that. And as opposed to kind of doing comparisons to how things are done in other languages or in other ways, we're kind of going through this curriculum with a kind of a very opinionated mind and kind of process in mind. But as the semester unravels, we try to teach them more about there are some other ways of doing these things as well. And finally, here is what we can do with those data. We can, for example, now that we have our data frame of all of the speeches, look to see if the length of the speech has been increasing throughout the pandemic, and maybe a little bit, but the R-squared is kind of low, but it's not bad. It does seem like the longer this is lasting, the more the leaders are having to explain themselves. Another thing we looked at was the use of the word social versus physical distancing. At the beginning of the pandemic, the word that was used more commonly was social distancing. But at some point, at least in some countries, that has turned to physical distancing with an acknowledgement of kind of the mental health unexpected consequences to mental health of the notion of social distancing, basically. So Nicola Sturgeon decidedly changed what she calls it. And so we basically get to look at that. But here, obviously, we have had to talk about text parsing, looking for the existence of a particular word, looking for the existence of that word, starting with a capital letter or not. And that's where the notion of regular expressions really comes into play. And finally, we do a text analysis as well. So once we've gone through the web scraping for the Scottish data, I did the web scraping for the UK data. So that's the speeches from 10 Downing Street. And then we actually talk a little bit about, at the end of the semester, bring this data back and talk about text analysis and calculate the TF-IDF, which is the looking at the term frequencies in two different bodies of text to see which words appear decidedly in one and not so much in the other. So you can see, for example, on the Scotland side, I mean, a lot of our students here are from Scotland, so they recognize the cities here that obviously the First Minister talks about, and I know Boris Johnson never mentions them, like Aberdeen, Lanarkshire, or whatever. But you can also see a few other things here. So if you look at the UK side, first of all, the first word is slide, because they constantly say next slide, please, because they use slides, but Nicola Sturgeon doesn't use slides. So that's like not a big difference in terms of context, but it is kind of fun to see. But the second word is a word that really shows the difference in approach of the speech style of the two leaders. In the UK speeches, there's a lot of, we will defeat this disease, we will defeat COVID. And the First Minister, Nicola Sturgeon, never uses that word. That is just not her approach. The approach for the briefings is like very scientific. Here are the hard facts, and here is what we want the public to do, versus there's a little bit of this like emotional, we're going to defeat it, we're the best in the world type of thing happening in the UK speeches. So we get a chance to look at these, but then also go back and browse the data to actually pull out the sentences. So you can imagine the thing here is we've now on the right-hand side gone through a lot of computational topics that we wanted to introduce to the students, all in the context of this case study. And turns out students love looking at things where things feel a little bit like you're picking on somebody or making comparisons. So they really get into figuring out, oh, I wonder why these words are showing up on one side and not the other side. And finally, I'll give one more example from the modeling side. So this is an example that is actually very classical, right? The notion of building a spam filter in the context of teaching logistic regression, for example. So we first start with, now that they've seen text as data, we first start with explaining, let's use an email corpus as our data and look at some metadata about it. You know, something very generic is how many characters, so how long was the email basically, and use that to predict whether the email was classified as spam or not. So this is a very kind of generic example of what is logistic regression and how do we do prediction. But the reason why we really introduced this topic is not to give a thorough treatment of logistic regression, really. That's probably something better reserved to a second course in regression where there's more time to devote to it, but really to talk about this table. The notion of a decision error, the notion of sensitivity and specificity, and giving students some intuition around loss functions. Depending on who you are and what your inbox is like, you might be more concerned with real emails accidentally going to spam or vice versa. So we start talking about how these might differ between people and how they might have kind of personal loss functions that are different. We don't end up really putting into practice how we would use different loss functions and how we would do prediction with them necessarily, but at least we start getting them to think about, just because the computer spits out a number to you and classifies an observation one way or another, doesn't necessarily mean that's a fact. There's a lot of assumptions that go into making that prediction. And in the looking further unit, this year students said we would like to learn a little bit more about machine learning. So we brought back this data set with the UK and Scottish data and actually built a predictive model for if you feed it a sentence, what would it predict? Would it predict that it's from the UK speeches or the Scotland speeches? And so these were the kind of the important variables. So the existence of some of these text strings. So you can see, for example, how physical distancing is one of the ones on the Scottish side, because they actually still use the word social distancing in the UK speeches. Slide is again up there. The word defeat is again here. So just thinking about, we've already explored this data. Now, how can we engineer features from these data to build a predictive model? And kind of to close the story, actually, we ended up not building a very good model. And the reason for that is that the sample sizes were very unbalanced and we ran out of time in the class for like also talking about kind of creating balanced resamples from these. And that would probably arguably be way beyond the scope of what this course was trying to achieve. But it is at least something that kind of draws home the point of there's some really important statistical concepts that underlie these models, even the machine learning models like balanced samples, that if you simply don't think about them, the model you build is not going to be good. There's like 5 times as many Scotland speeches than UK speeches throughout the entire pandemic. So whenever you ask it to predict something, it more often predicts Scotland just by the nature of the sample sizes, which obviously is ridiculous in terms of what we were trying to achieve. But at least getting the students to the point that they can sense that could be an issue, I think is a good enough statistical goal for an introductory data science course where they're also learning so much computationally. So now that I've given you an idea of what are the sorts of things they're learning in the class, I'd like to give a few tips about like how do you make all of this work and fit it into a semester, because that's a question I get asked a lot. So one of the things is going through these kind of extensive examples that I explained to you in lecture means that there are some things that we're not spending a lot of time on during kind of face-to-face hours or lecture time, which is repetition, for example. You know, you build one visualization, just because you taught students to make a single bar graph doesn't mean they've learned it. It just means you've mentioned it once. So you need the opportunity for them to actually get more practice with some of these kind of elementary but also important components of learning a new computing language. And that is something that happens at home. And in order for that to happen at home as part of an assignment, I think it's really important to try to give students some opportunity to get immediate feedback. And that immediate feedback, if it's only the R errors they get, they can get quite kind of discouraging, because it's really hard to read those errors and see what you've done wrong. So I use the LearnR package to build these interactive tutorials where basically, depending on the mistake they make, hopefully, if it's one of the ones I predicted they might make a mistake with, they get a piece of feedback that sounds more like what I would tell them if I was looking over their shoulder during class and they made a mistake, and I would say, hey, is it possible you forgot to put a comma? Or did you really mean fill when you meant color, or something like that? Another thing is then getting them to reflect on this. So they go through these interactive tutorials, and they also take weekly quizzes that are created also with LearnR. But ultimately, we want them to not just go through that experience, but be able to reflect on it a little bit. So one of the methods that's used more commonly in writing courses, actually, or literature courses, is this notion of a minute paper, where at the end of a class, you ask students, okay, now we're done talking, take a pen and pencil, and for 1 minute, just reflect on what you learned, what was confusing, what worked, what didn't, do you have any questions? And you get them to kind of just like do a brain dump for just 1 minute. So what I ask the students to do at the end of each of these weekly quizzes is give them a form entry where they can do that actually. And once they do that, they give me a paragraph of whatever was confusing to them or what they feel like was easy. But I had like almost 300 students in my class, so that doesn't mean I actually can necessarily read all of these paragraphs. So one of the things I do is then take those paragraphs and just like do some very rudimentary text analysis on it myself. So simply looking at bigrams from free entry text like this can be really informative about what students are confused with. So sometimes they just tell you which question they missed, which I could have gotten simply from the quiz results as well. But they also say things like join function, for example. That was clearly that week, join functions were difficult for them. And then also another thing that comes up is the word, like the bigram feel like, which people generally use when they probably were saying, I feel like this wasn't clear, as opposed to like, I feel like this week was such a good week for learning. So if anything pops up to you from here, you can then just like simply look for those phrases and read those paragraphs and probably get enough information about how to structure the next week's class. So this sort of information on a weekly basis is so helpful for figuring out what you should start saying the next week. So I usually start saying, these were some of the topics that came up from your quiz reflections. Let's do a quick review on them before we move on to new material. Another thing I would recommend is making room for creativity where possible. So one of the ways you can do this is an open-ended project, but that's easier said than done. I mean, if you have the resources to manage the open-ended projects, I think this is a fantastic way to end a data science course, or really even an applied statistics course, anything else. Ask the students to find a data set and do something with it that they've learned in the class, and not apply a particular method, just really do anything with it. But these can be sometimes hard to manage. So even if this is not feasible, or it is, as additionally, you can also think about adding creativity in other ways as well. One of the things I really like for this is, for example, is asking them to make a really ugly ggplot too. Because asking people to make something pretty is actually asking a lot of them, because the notion of what's a beautiful data visualization is a hard thing to settle on. But asking them to make an ugly data visualization turns out really gets their juices flowing. So I'll give you some examples. This is from a student from last year, actually, who wanted their visualization to look like an iron brew tartan. And then this was something from this year. So the thing is, actually, if you ask me to replicate this visualization, I have no idea how to get that picture in the background of a ggplot too. I'm sure I can figure it out, but I don't know. And we've certainly not taught the students to do these things. And the goal isn't that they make these silly things going forward, The goal is that they understand that you can customize the heck out of a visualization if you want to. Here's some silly stuff I did, but at least in order to be able to do that, I really needed to learn how to read documentation. And next time I want to do it for real, I know where to get started. And the other thing is allowing for peer review where possible. Not only does it allow you to expand your grading power, if you will, because now you have an army of others who can provide feedback, but also the nice thing about doing peer review is that the good things that can come out of each of the students' learnings tends to be contagious. As in, when a student reads somebody else's work and they see something good in it, they usually take that with them and say, hey, that was a good idea. I wonder if I can apply it as well. I think rarely do they see something bad and say, let me replicate that as well. So I think the risk of them learning something wrong from each other is very low, but the potential of them learning good approaches from each other is high. So one of the places I use the peer review is at this stage of the project proposals, where we allow them to kind of peer review 3 other proposals, give some feedback, and also tell their peers things like, what would you like to hear about if you had to sit through the 5-minute presentation at the end of the semester? Because you will have to sit through it. So you might as well tell them what will be an interesting thing for you to hear about. And finally, as much as possible, bring real workflows into the mix. So one of the things we do here is, as I said, everything is a GitHub repository. And if you are a GitHub user, you probably know that one of the things you can do is open issues, for example. So when we do their project proposal reviews, I actually create an issue for everything that they could improve on. And we teach them how to close those issues with specific commits. And in fact, we allow them to resubmit their proposal if they want to increase their grade a little bit. So it gives them a motivation to do that, but they learn a very real data science workflow of making deliberate commits to address a particular issue that someone who reviewed your work has raised. In terms of how this is all happening, really on the student side, they just go to a website and type code, right? So my goal often is like, how can we get them to start typing code as quickly as they could fire up Netflix and start watching a show? So this could be RStudio Cloud, or it could be a server-based access to RStudio, but the notion is that they just go to a website and things kind of work for them. They learn a lot of R packages, but really underlying them all is tidyverse and tidy models for what they're doing with data, and then R Markdown for how they're building their reports. And they're using Git and GitHub along the way for both version control and collaboration. To submit their homework, they have to push to GitHub. So it just becomes a thing that they learn to do pretty quickly. From the instructor side, it's like a Pandora's box. There's a lot that you probably need to do. And so what I want to do is, instead of overwhelming you with like all of the tooling that's helpful for running these things, this sort of a course kind of effectively and efficiently, I've provided all of the contents for this course in a project called Data Science in a Box. So this has not just the course content, so slides, videos and whatnot, that's all open source, so you can reuse however you like. But there's also some write-up you'll see under the infrastructure side about like, how do you set up teaching on GitHub and stuff. So there's some write-up there about that as well. And we also have a community on Slack of using these materials either in full or in part, who ask questions about like what they're doing with that. So if you're interested in teaching something like that or learning more about it, this is the place to go. I also have provided the link to my website from last semester's course, not because there's anything in here that's not in the other resource, but mostly because I personally like seeing how things get presented to students as opposed to presented to other instructors. So that might be inspirational for that. And finally, we have a paper about the pedagogy behind this course, That's on the Journal of Statistics Education. Actually, the journal just got renamed to Journal of Statistics and Data Science Education, so I should update that just with this upcoming issue. And I wanted to draw your attention to their upcoming special issue on computing in the curriculum. So 10 years ago, Deb Nolan and Duncan Temple Lang wrote this paper that was really kind of very influential in terms of how a lot of stats educators have thought about bringing computing into the curriculum. This is their insane Venn diagram about what computing technologies they thought would need to be prominent in the statistics curricula. And you can look back to see in the last 10 years which of these happened and didn't happen. And there's a series of webinars that Cause is putting together, that's on the bottom link there, about some of the papers from this special issue. So if you're interested, the issues, the journal is an open access journal anyway, but there's also going to be further discussion about some of the papers that are kind of looking back at this paper 10 years later and talking about what actually did happen in stats education. So that's it from me. The slides are on the top link here. So if you're interested in getting back to any of those things I linked to or looking through the examples again, you can add them there and I will be happy to answer any questions.
Oh, thank you very much, Mina. I think it was inspiring and super interesting. So if there are any questions, you can either unmute yourself or write it down in the chat. I can read it for everyone.
Hi, can I ask a question?
Yeah, please do.
Hi, Mina. I met you before at a conference, and so this is an amazing talk. It's very inspiring. So I have a question. It seems because you're using technology in such a good way that maybe for you the transfer to teaching online was easy or easier, but I'd just be interested to know how you had to adapt the course to deal with teaching online, because obviously it's something we're all grappling with at the moment.
Yeah, I have to say you're right. It actually was, well, easy is not the right word, but certain things did not have to change, I think, and a lot did not have to change in terms of what the students were doing. So what was hard was making videos for me, but I feel like that's like a side topic, as in like we could have chosen to do all the lectures on Zoom. As a school, we decided that wasn't like the best way to approach this, but I'll set that aside because that's more about content delivery. But when you think about what the students need to do as they learn, and then also to submit their work and stuff, that was all happening online anyway. So in fact, in the student evaluations that we've gotten, both in the midterm and the end of the semester, even the students remarked that because they hadn't taken this course before, they thought it was very well adjusted to online teaching, but actually I hadn't really changed a whole lot since the collaboration already has to happen online on GitHub. So when they're doing teamwork, they already had to push to the same repository and sometimes resolve merge conflicts anyway. So we didn't change anything. What did change is one of the best ways, turns out, to get students to physically work together is to make them be scared of merge conflicts, because like they would actually meet up in person to not have to work through merge conflicts. But so they were doing it on Zoom now. So they would hop on and do it on Zoom. And in class, when I teach in person, I hear them say, please, nobody push. I'm going to push now. But at least they're talking to each other. And so I think a lot of that was happening as well. We also held weekly workshops, which would be the lab sessions, in where they used to do things in person. This time it was in breakout rooms in Zoom. But again, ultimately, they were all accessing our studio online anyway. That didn't change. And also they were pushing to GitHub to collaborate anyway, and that didn't change either. So what a lot of the students would do in person is one person would be the typer for that day and everyone would huddle around their computer. And on Zoom, that just meant that was the person screen sharing and everybody else was kind of just like trying it on their own and giving feedback. With slightly more dysfunctional teams, some students end up being not contributing as much. But my observation is that the rate of that happening didn't change from online to in person. It's just like some students don't contribute as much. That's just a fact. And that wasn't necessarily diminished, except in some circumstances of bad internet connection for students, which was really, really difficult to work through and made some of the stuff difficult. But I don't think more so for this class than any other class.
Okay, thank you.
Any other
Can I ask
questions?
a question? Sorry,
Yeah, go ahead.
Thanks. That was a really interesting talk. I suppose one thing I was just interested in was so the way that you framed the talk and the way you introduced the material was you know, it was really interesting, and there's very clear differences there from a traditional stats talk, and you were quite clear about those. But I was just wondering, was it a challenge to figure out like what data science actually was, right? Lots of people talk about data science, but I've never really seen, a definition that is particularly compelling, just like a very clean, concise definition. So I was just wondering, how did you decide what data science was as opposed to intro stats, and how, what was the thought process involved in making those kinds of decisions?
Yeah, so I'll give you two answers, one the good answer and then one a practical answer. So I think the good answer is I trying to answer that question philosophically, I find is like a good academic exercise, but ends up being difficult to put into practice because everyone has opinions about it. But one of the things we did as part of the paper I mentioned is we actually surveyed a number of introductory data science courses from a variety of universities, some in the US, some in the UK, some public, some private, some big schools, some smaller schools, and took a look to see what do they teach, and took a look at the distributions of those, and then use that to guide to form the curriculum here as well. And that's not to say we went with the averages per se, but it was a nice way of figuring out how are others defining data science. So I would say we define data science empirically in a way based on what was out there, plus based on just what are some of the tools that are being used a lot. So I am in a privileged position of also working with our studio, so I get to see and I follow just the issues on some of the tidyverse repositories, for example. It's such a good way to find out what people are confused with, but what they're confused with tells you what they're trying to do. So what are data scientists in practice trying to do? And I think that's, again, another empirical way of thinking. I think we should teach students what to do when data isn't in a tabular format. That's not some advanced topic. Turns out you're probably going to need to do that in your first data science job out of college. It's not that advanced. Versus some of the predictive modeling topics actually are, and a lot of traditional stats courses do that and not the data cleaning stuff. Now the practical answer, so I think that's the good answer, but the practical answer is when you want to put on a data science course, all you need to convince is whoever is approving courses, So I think you can be a little bit opinionated and iterate based on how things are feeling. So I've taught this course for many years at Duke, and I started it as a first year seminar that was 18 students. This year, they're teaching 3 sections of this course each semester, and they're replacing some of the introductory stats courses with this curriculum because that's what students are interested in, both who are stats majors, but also who are other majors who are just taking this as their quantitative requirement. So I think I was able to define what it is because the only person I had to convince was the chair or whoever, and then whoever approves the courses. So you don't have to convince the whole world about what data science is.
Well, that's a great answer. Thanks. I think you kind of referred to it then, but if I can just ask you a very quick follow-up question. So you said, you did the empirical survey, which is great. And then, I think you maybe implied anyway that you liked some courses better than other ones. So without having to mention any names or anything like that, I mean, is there anything that you saw being done that you wouldn't recommend, or that you think maybe is kind of the wrong direction to go in?
Yeah, so I think some of the courses we looked at just had a name change as opposed to content change. So there was a lot of probability theory. Now, this is not to say probability theory has no place in data science. I think there is a place for a probabilistic machine learning course, for example, that's potentially for upper level undergrad or master's or PhD. So this is not to say probability isn't important, but of all the things to teach in the intro course, why go into that? Because a nice thing about this curriculum is there's no calculus prereq, for example. It's really hard to teach good probability without a calculus prereq. So I think those were some of the things that I thought was unideal. Another thing was some courses don't even touch on data science ethics at all. And I think that I wouldn't want to claim that like my students emerge out of this like being aware of all the ethical concerns, but just knowing that there is such a concern, I think is so important early on. So I think there's stuff like that, and also just the computational tooling that's used, the emphasis on reproducibility and stuff. Some courses did a lot more of that than others.
That's brilliant. Thanks, William.
You're welcome.
And we're actually running a course here at Maynooth that's to some extent modeled on Nina's setup. So yeah, it's
great.
I'm not teaching it myself, but I think they have like 60 or 70 people, but you know, we could take more. It's probably not as computationally intensive, but you know, we're kind of working on it.
That's great.
Yeah.
I'm glad to hear it's working.
I think so.
Yeah, if I can just throw it in, then yeah, I'm teaching a stats module on a data science master's course. So kind of, I guess at the other side of it, where kind of students who are very comfortable, maybe with a lot of the students who take the master's program are very, very good at formatting data and using things like, you know, SQL relational databases to merge things together. But then what they want to know is, you know, once I've done that, you know, if they're coming from a job, right, basically they've done that, and then somebody else has said, okay, I'm going to take this away and analyze this and have fun with this, and they're like, you know, so the next step for them is to kind of think about those things. But I really, I think seeing this talk has kind of helped me to understand, you know, pipeline a bit better and to kind of think about those elements as well. So yeah, so definitely really useful.
Okay. So it's time to finish off this session. Thank you very much for attending this webinar, and first of all, thank you to Mina for her presentation. We all thought it was great. So that's a virtual round of applause to Mina.
Thank you very much.
I shared the link to her presentation in the chat, so you can access it. And thank you, everybody. Thank you for being here.
Wonderful. Thanks for having me. Have a good rest of your day. Bye.